First, I have one announcement. Since more students showed up in the offline class on Monday than expected, I had to change the room because it was a bit too small for all the students. I couldn't go to all the tables and talk to the students. That's why from next week on, we will be in another room in 5101. That's a little bit bigger, and the only other room of the size we need that is free at this time. And I will send an email on Monday reminding you of the room where we will meet, and I will also write it in the e-learning course. And for today, what we did so far, we finished the theory of chapter 1, and we started solving some problems on Monday, which went quite well. And some of you already started with problem 110. I will just quickly discuss this and do the computations for you to have another example of this type of exercise. So what do we have here? We have a platform that rotates with constant angular velocity and omega L, and a person walking outwards in radial direction. And the person starts at the distance of r0, initial position, and then it works with constant velocity vr. And again, we are supposed to find absolute velocity and absolute acceleration. With the offline class, we already discussed the free body diagrams or diagrams including velocities and accelerations. And but I will repeat it for all of you. So as we already discussed on Monday, it's important, or it helps you a lot if you draw two separate figures, one for the velocities and a second one for accelerations. So this is our radius. The circle above is the person walking. The radius changes over time. And then our leading velocity, the simple motion that we can see, that we can describe as outward observer, is the rotation of the platform. And the platform rotates with omega L. Rotates with constant angular velocity, meaning that the leading angular acceleration is 0. Then what do we have for the velocity? We have a velocity vector perpendicular on the path. And in general, we have two components of the acceleration, a tangential and a normal acceleration, AL tangential and AL normal. And our relative motion is the person walking with constant velocity outwards. So it's walking in this direction. We are, as depicted in the figure given. And then again, this person walks with constant velocity, meaning that the acceleration is 0. Now, since our leading motion is a circular motion, we have to consider Coriolis acceleration. And we also discussed and practiced that on Monday. How do we find the direction of the Coriolis acceleration? We need our right-hand rule. Our thumb corresponds to the axis of rotation of the leading motion, omega L. So this means our thumb points outwards of the plane of paper, upwards, right? So fingers indicating the direction of omega L. Same as in statics, engineering mechanics 1, where we discussed the direction of the moment. Then our index finger points in direction of the relative velocity, the green vector. And our middle finger shows the direction of Coriolis acceleration. So again, thumb corresponds to the axis of rotation of the leading velocity, index finger points in direction of the relative velocity, and our middle finger indicates direction of Coriolis acceleration, pointing that way. Okay, once we were able to draw the figures, we can use our first page in the formulary deriving velocity and acceleration components. First, for the individual parts of the motion, we will start with the leading motion, which is our circular motion of the platform.
Professor, I have a question.
Yes.
I just wanted to confirm that whenever deciding the leading velocity or the leading motion, that's the observer which is observing the body, for example, not from the inside, from the outside, right?
Yes, from the outside. Exactly. Yeah, that's correct. Okay, our leading velocity for a circular motion can be obtained by angular velocity multiplied with the radius, and keeping in mind that our radius is time dependent. Our tangential component of the leading acceleration is obtained by alpha L times r, but since alpha is equal to 0, the tangential component is 0 as well. And the normal component, omega L squared times r. Then the relative motion our green vectors. The velocity Vr is given, and it's constant. That is stated in the problem description. If the velocity is constant, the acceleration is 0. And we have to derive an equation for the distance the person walks, our time-dependent radius. And that again, I will just quickly switch to the formulary. First page of the formulary. This equation right here, we have our position as time-dependent variable, which is equal to our initial position plus initial velocity times or multiplied by the time. So this equation is what we need here as well. So in our case, it's not x, it's r. R is equal to r0, our starting position, the starting position of the person, plus our velocity, which is our constant velocity of the person walking, times t, and acceleration is 0. So last and third part we need is the Coriolis acceleration. We simply have to state the equation, which is also written in the formula 2, omega L Vr. Omega L and Vr are given, so we do not have to compute anything else here. Once we have the components, we can compute the absolute acceleration and absolute velocity. the absolute motion. We'll start with the velocities. And again, we will first state the general equation as vector equation. So it's VL plus VR, vector addition of leading and relative motion. In our case, leading and relative velocity vectors are perpendicular to each other. Then it's quite simple. The absolute velocity is obtained by VL square plus VR square, and then we build the square root. And we can substitute our values. Omega L square R0 plus VR times T square plus VR square. So there are no numbers given. And then this is our result.
Excuse me, miss, I have a question. So in an exam setting, are most questions going to be like this, as in like no numbers given, or are we going to be given numbers and we have to find a solution?
Both is possible. There probably there will be problems given with numbers, and there might also be one problem without numbers, so with only variables. Both is possible. Okay. And then for the acceleration, we start out with the vector equation AL plus AR plus A Coriolis. Our relative acceleration is 0, and our tangential acceleration is 0 as well, leading tangential acceleration. So we only have two vectors, again, which are perpendicular to each other. Then A is equal to ALN square plus A Coriolis square, and that's omega L to the power of 4 R0 plus VRT square plus 2 omega L VR square. Okay. Are there any questions regarding this problem? Okay, we will do another exercise regarding chapter 1 in our Monday class, where you have time to solve it on your own. But again, even if the system might appear a bit more complicated, the approach is always the same. It's one leading motion, it's one relative motion. There might be a Coriolis acceleration. We have to do the vector addition to find the absolute motion. Today in our class, we want to move on in our script. So I'm changing to the script. That's where we stopped. No, that's where we stopped. So now we are on page 7, chapter 2, kinematics of rigid bodies. So there's some theory first that we have to talk about, and then we will have a look at first few examples. So what is a rigid body? You do know the definition of a rigid body from Engineering Mechanics 1. And this is a system of an infinite number of particles whose relative distance remains unchanged. Or other definition, it's an object with a specified mass and with spatial dimensions, a length, a width, a height. So in chapter 1, what we did there, we described one point And the example we just did, this point was the person. We described one point on two different systems, on two different bodies. So first we described the point as rotating on the platform, and then we described this point walking along a straight line. But in both cases, we had 2 points, one point that we described on two systems. Now, in case of rigid bodies, we are describing 2 points on one rigid body. So 2 points whose distance remains unchanged. Okay. And again, similar to chapter 1, we have 2 simple forms of motion that we can describe using our mathematical equations. So the first one is the translation. Here, okay, I'm talking about this. So in case of translation, we have no rotation of the body. So our object, our rigid body, moves with a specific velocity and acceleration along a certain line. Whichever it is, does not mean it moves along the x-axis or along the y-axis, but it moves on a straight line somewhere through our 3-dimensional or 2-dimensional domain. Could be like just use a rectangle to describe our object, like this. And then we have to pick 2 points on this object, on this rigid body. For example, like this, point A and point B. And now this object, this body, moves with a certain velocity and acceleration, covers a specific distance, and let's assume it moves in this direction. In general, these are vectors. Of course, it could point in x, y, and z direction. Could have components in x, y, and z direction. And then later in time, this object may be here with point A and point B. And to describe the motion of this object, we can describe the motion of one of these points. For example, the velocity of point A is given. And in case of a translational motion, point B moves with exactly the same velocity and acceleration. VB is equal to VA. That's what is stated here. In case of translation, all points on the rigid body move the same velocity and acceleration in the same direction. That's our first simple form of motion. The second simple form of motion is our rotation, corresponding to the motion along to our circular motion in chapter 1. So in case of the rotation, we are assuming that we have a rotation about one point of our object. For example, this point A. So again, I use the same object, our rectangle. This is point A. This is point B. And now we assume that our object rotates about point A. Just drawing a hinged support. Then sometime later in time, the object might be in this position right here. And our point B could be here. Then if our object moves, rotates about this point A, then this point A has no velocity and no acceleration. It's not moving anywhere. And our object itself covers a certain angle, angular velocity, has an angular velocity and angular acceleration. Point B moves along a circular path like this. With omega and alpha. So our object rotates with omega and alpha and covers the angle phi. Now describing this motion is very similar to describing a point mass moving along a circular path, circular motion of a point mass. And if you have a look at these equations here, you will recognize them. So what it says is that the distance, the arc length covered of point B can be obtained by the distance between those 2 points, A and B. A is the center of the circular path and the angle covered. The velocity, again, is distance AB corresponding to the radius of our circular path times angular velocity. And tangential and normal components of the acceleration, again, depend on the radius of the circular path and the angular acceleration, or the square of the angular velocity. These are vectors, and they point in the same direction as in chapter 1, of course. Velocity tangential on the path, tangential acceleration is tangential on the path, and the normal acceleration points towards the center of the circular path, which is point A in our case. Okay. Then, if we want to describe a general motion of an object, we do have to do a superposition of these 2 types of motion, translation and rotation. That means that we can describe the kinematics of any arbitrary object by translation as point A and rotation of point B about A. That's what's stated right here. So, and that's the main difference. In case of a point mass, chapter 1, we say we have a leading and a relative motion. But our leading motion can either be circular or rectilinear, and our relative motion as well. It can either be circular or rectilinear. Both is possible for leading and relative motion. In case of a rigid body, we always have to superpose translation and rotation. So it's not leading and relative motion anymore, it's translation and rotation. That's the main difference. And once you understood that and memorized that, you will be easy to solve these type of problems. And no, point A is not at the center of the mass. It's some arbitrary point, and our object rotates about that point. In my example, it's in the upper area, upper half of the rectangle in this case.
Professor, so the previous examples that we did with the rotational bodies, were they not rigid bodies, or I'm a bit confused?
No, because for the person, the person was a single point walking on the platform. So there was no rigid connection between platform and person. Okay.
Okay, understood. Okay.
Okay. Okay, and now we are describing one object rotate or moving arbitrarily through our two-dimensional domain. Okay, let's move to the next page. Now we will derive the equations we needed, similar to what we did for chapter 1 last week, where we had this robot arm describing the position of the workpiece or the clamp. Well, for example, I will draw something here. It has nothing to do with this part, so don't draw what I'm drawing, okay? Just referring to the question in the chat. We did this example right here. So describing the motion of this point, the workpiece or the clamp of the robot arm. Now, our objects are connected, but they are two types of motion taking place in this situation. And we can describe this point as one situation. So this would be our, had here this omega as this. Now describing this point on this rigid object, stiff connection right here. And then we added a second system, subsystem, like this. Okay, so we consider this to be two different systems. We are describing this one point here on two different systems. The first one is our leading, and the second is our relative motion. That's what we do in point kinematics. And then we will do this in just a second. I will derive that in for rigid bodies. We will not break it down to these different subsystems. It will stay, it will be considered as one system throughout the whole description, mathematical description of the object. Okay, our example. We use this this block, and now let's assume looks like this. And again, I will pick points A and B, and we want to describe the motion of point B. Okay, perfect. So now, first of all, we need to know the position of our block, referring to a fixed frame of reference. Radius of point A. Now, again, to describe the motion of point B, we have to, well, the absolute motion of point B, I will use red again for absolute motion. You have the color coding. And then we do the vector addition, the superposition of translation plus rotation. So we say, okay, our object translates as point A. So we might have a velocity VA here and an acceleration, absolute acceleration of point A, maybe pointing over here. And then we add the rotation of point B about A. We need the angle covered, and we need omega and alpha. That's our general diagram. We will just draw when the object moves through our two-dimensional plane. But for the colors, again, red is the absolute motion, purple translation, green rotation. In 1D, purple was leading and green was relative motion. Okay, that's our starting situation. Now I will draw these 2 points, A and B, and how they move through the plane. I will not draw the box around it because it will just become too full. Yeah, our figure becomes too full if I always keep drawing this, the object itself. So I will draw a Buff's figure again without the box. And now let's say we are here, we are at time t. A at time t and B at time t. And now we only have a non-moving observer standing here. Or outside non-moving observer. So now this observer wants to describe the motion of point B. Similar to chapter 1, we will derive this for distances traveled. Okay. So what he wants to describe is this motion. Distance from our reference point to the current point at the time t. So, but this point performs an arbitrary motion, moving throughout this plane on an arbitrary path. So we are not able to describe this mathematically. So what we do is we describe point A. We know the distance there and how it moves. And from point A, we do know the distance to point B. And we know that the distance never changes, since both points are on a rigid object. R, B, A of t. Now, later in time, point A may have moved over there. A at time t plus a little bit later, t dt. And if the motion would be a pure translation, then point B would be here. So this is the distance point A has traveled. dRA, the change of position of point A. I'm right now I'm describing the motion of these 2 points. Imagine that they are on the same object as drawn above, and now they move over here along this purple line. That's the first part of the motion. Then point B has moved over here due to the same change in position. Translation means both points move identically with same distance, velocity, and acceleration. But in reality, it's a general motion, and this point B has also rotated about point A, meaning that it's here. That is point B at t plus dt, t plus a little bit later in time. So again, this is RBA at time t plus t dt, the distance between these 2 points later in time. But of course, both of them are on a rigid object, so the distance does not change. RBA is constant over time. But what has changed is the angle here, d phi.
Excuse me, Professor.
Yes?
What's that in the first diagram? What's that symbol before A?
An A, a small a, acceleration of point A.
Oh, okay. Okay, yeah, thank you.
Then this point B has moved over here due to the change of orientation between the distances. And the absolute change in motion of point B is this, drB. Now, for the to describe this mathematically, we need to do the vector addition. So for the first part, we can simply say, okay, we want to describe the position of point B, and we can describe this by simplifying our general motion into a translation and a rotation. So we say B translates as point A, and at the same time, B rotates about A. It's important that you write these in the correct order, BA. It's not AB. When you write it like this, it means B rotates about A. Okay? So B moves translational as A, and at the same time, B rotates about A. So as I already said, the distance between these 2 points, just the distance AB, is constant over time. The length, the distance. But the orientation changes. And since it's a vector addition, the vector components change as well. Due to the rotation, they change in direction due to the rotation. due to omega and alpha, angular acceleration and angular velocity. So example, if this is our vector RBA, then these would be the components, y component and x component, which we could state in our vector. And a little bit later in time, this might be the distance RBA. This is A, this is B. Then the length of the vector, the absolute value of this vector, is constant, but the components have changed. So if you write it as a vector with your components, the components, x and y components, or horizontal and vertical component, change over time, but not the absolute value, the length of the vector. Okay, if we can state this for the current position, we can also state this equation for the change of this position. drB is equal to dRA plus dRBA. And then it's identical to what we did in chapter 1. We can build the time derivatives. drB dt results in the velocity of point B, and the velocity of point B then is dRA dt plus dRBA dt, or VA plus VBA. Okay, and since it's a change in distance along a circular path, we can apply the equation for the arc length. dRBA is equal to the radius, distance between these 2 points, times the change in angle. So to compute the velocity of B about A, it's the velocity due to rotation. So let's have a look at this time derivative. Then it's AB, it's constant over time, and we only have to derive the phi dt, and we obtain AB times omega, and that's exactly what we already learned in chapter 1 for circular motion. Velocity due to rotation is radius times angular velocity.
Excuse me, Professor.
Yes.
This is a phi?
Yes.
Yep, got it. Thank you.
The R is distance. RBA is the distance between point B and A, as in the figure above. Okay, now let's state the important equations, the equations we need to solve the problems later on. So the first one for the velocity in general, we pick 2 points on the same object. And then we say point B moves translational as point A, and B rotates about A. Well, as drawn in the figure, RA is the distance from our reference point to A, and RB is the distance from our reference point to point B. Then VA is a translational velocity. So I need some information, which direction it travels, how much distance is covered over time or something like this to compute the velocity, or it might be given in the drop-in description. And for the rotational velocity, when we can compute it as already learned and written in the first page of our formulary, radius times angular velocity. And this velocity, VBA, is perpendicular to the distance AB, our radius. So same as before. And for the acceleration, AB can also be computed by translation as A plus rotation of B about A. And the rotational component of the acceleration consists of a tangential and a normal component. So also that's the same as before, just radius times alpha for the tangential component and radius times omega square for the normal component. Tangential component points in the same direction as the velocity, perpendicular to the radius, tangential on the path. And the normal component points towards the center of the circular path. In our case here, in our definition, it's point A. And again, if we know the components of the rotational part of the motion, we can build the absolute value ABA, but that's not necessary in the most cases. Okay, when we have that, we can move on to the next page.
Wait, Professor, can you go back? I'm still copying.
Okay.
Okay, thank you.
Okay, so the last part, or no, the next part is that we can talk about some special body points. Some points we can pick on our object, on our rigid object, that helps us describe the motion, because it's we know the motion of this object, of this point, and then it makes it easier to use this as our point A, for example. So they are just named here. The first one is a pivot, which is point connecting two bodies. Then this would help if we have several bodies connected to each other to use this point. When we describe the motion of this point, it will be identical on both subsystems, on both rigid objects. Okay, so we'll see that later on in different examples. Then also a sliding joint, we know that on a sliding joint we only have a rectilinear motion. So it's simple to describe the motion here. then often the center of gravity is used as one of the points, for example, when describing wheels or cylinders moving, then it's quite easy to see how the center of this object, the center of gravity of this object moves. Then the velocity pole is quite helpful, because here the velocity in this velocity pole is 0. And then this also helps describing the motion. We will have a look at this in just a second. And then there's another point, the acceleration pole, which is more or less the opposite of the velocity pole, because in that point there's no acceleration, but a velocity. We will not need the acceleration pole in our class, but maybe you may come across it later on or in your work life. Okay, but for our velocity pole, I have a simple example here. It's a cylinder rotating and moving along this surface. So this straight line is the surface, and then this is our cylinder rolling along the surface. And then we have a velocity of the center of gravity. And if the cylinder rotates along this straight surface, our velocity, our center of gravity moves rectilinearly. It's a translational motion. The center of velocity moves like that. It's not rotating. It stays in the same height, distance r, distance the radius to the surface. Now, if we want to describe other points, for example, this point right here and this point there, we can use our standard approach that we just talked about. We can say, okay, we pick 2 points on this object, and now we can say, for example, this is point A, and this is point B. We can say, okay, point A moves translational as point C, our center of gravity, because there we know the direction of motion. So this is our translation. A translates as point C, and B also translates as point C. And then at the same time, the cylinder rolls, so it has a angular velocity omega, rolls in this direction. Then we do have a component, a velocity component due to rotation. Point A rotates about the center of gravity. And then the velocity due to rotation is tangential on the path, pointing this way. We AC, because A rotates about C. Same for point B. B rotates about C. BC. And then we can build the absolute values by superposition of these vectors. For point B, that's quite simple, because the vectors point in the same direction. That's the absolute velocity of point B. And for A, we have to do the vector addition. So VA points that way. No. Oh, okay. Now, that's how we can describe the absolute velocity of a rigid object. Now, if you want to find the velocity pole, we have to know the direction of at least 2 velocity vectors, for example, A and B. And then we can draw a line perpendicular to the velocity vectors. Here. And here. And where these lines intersect, we find the velocity pole. So this is our velocity pole. And now we can simply always remember that in case of a rolling cylinder, tire, or whatever, our velocity pole is in the contact point between cylinder and surface. And then the advantage of this velocity pole is that it's quite simple, easy to compute the absolute velocity. It's stated here in this orange box. So for example, for point A, the velocity of point A is obtained by computing the distance from A to P, our velocity pole, multiplied by omega. Same for B, it's the distance between point B and P multiplied by omega. The velocities in direction, they are always perpendicular to the radius, distance between velocity pole and our point of interest. And they can be described as a pure rotation about the velocity pole. We do not have to do a superposition of translation and rotation. If we use the velocity pole to compute the velocities, it can be described as a pure rotation about this pole, this velocity pole. But a very important information here is that this is only that it only works in case of pure rolling. Pure rolling means that there's no sliding, slipping of the wheel or the cylinder on the surface.
I'm sorry, Professor. Quick
Yes.
question. The velocity pole won't work when we have moving ground, right?
Yes.
And when P has a the surface has a
When there's
velocity.
a relative velocity between cylinder and surface.
Yeah.
Yes. So it only works if the cylinder rolls along our surface.
Thank you.
Yeah, there's a question. What is VI? That's a good question. Point of intersection of all straight lines perpendicular to not an L, perpendicular to the velocity vectors, and that's A, B, etc. It refers to all the velocity vectors. So perpendicular to VA, perpendicular to VB, and if we would add more velocities, then to these DEF, whatever. The last part is that the advantage of the velocity pole is that we can, it looks like an L actually, maybe it's a small L. The advantage of the velocity pole is that the velocity, the absolute velocity of this arbitrary point A or B, as in this example, can be computed by the equation for the velocity of pure rotation. So distance between the points as our radius multiplied by the angular velocity. But this approach, this only works when our object, our cylinder or our tire or whatever it is, performs pure rolling. That means that there is no sliding, no slipping or whatever between the cylinder and the surface. Because if it slides, then the velocity is not zero in this contact point, in the contact point between surface and object. Then it doesn't work because the velocity pole only exists or is a point at which the velocity is zero in this instant of time. Okay. But of course, velocity pole helps solving problems relative to surface, yes. Velocity pole helps solving problems, but we can only compute velocities. We are not able to compute accelerations using this approach. It only works for velocities, so that's important. And if you don't like using the velocity pole, that's absolutely okay, because you can solve any problem with the standard approach, translation plus rotation. You do not need the velocity pole in none of the cases, none of the problems. You can if you like to, and it might simplify, or well, not really simplify, but you will be faster solving the problem, but it's not necessary. You can always solve it without velocity pole. Okay. Let's have a look at the first exercise of chapter 2. It's exercise 2.1.
Professor?
Yes.
So in this case, the point P will have 0 velocity, and the point B will have 2c velocity.
Yes, exactly. Down here in P, BP is equal to 0.
Okay, thank you.
And yes, to the question in the chat, the velocity of any point on this object, of course, on this object can be described as pure rotation about P. We only need the distance between the 2 points. And then we know the size of the velocity and the direction, because the direction of the velocity is perpendicular to the distance drawing the line between the 2 points. There was another.
Professor, just a quick question. So over here, the line intersect going through the middle, BP, that's the velocity pole, and the AP and the intersection. So we have 2 poles in this diagram, or?
No, P is the velocity pole. And there's 1 point P. So here, this is our velocity pole. Down here, the contact between object and surface.
Okay, so it's a product of the cross section of both of these lines, for example.
It's the intersection of these 2 lines that are perpendicular to our vectors VA and VB. But of course, here we derive the position. Now for these type of problems, a rolling tire or cylinder on a surface, we always know from now on, we always know that our velocity pole is there. Yes, in this case, a cylinder or a tire, like something with a circular cross section, the velocity pole is always in the contact point with the surface. If we have different problems like beams connected by joints, we might also find a velocity pole there, but then of course it's somewhere else. We will discuss that later on. But for this situation here, when you have a problem like this, we know the velocity pole is in this contact point. Okay, now for the first exercise. It's slow today. Okay, problem 2.1. I'll just have to quickly copy it into our lecture notes. Okay, so what do we have? We have a car driving with a velocity of 10 kilometers per hour. And this car accelerates with 2 meters per square second. And we have to find the velocity and acceleration of the points A, B, C, and D as drawn in the figure. The radius of the tire is given with 31 centimeters, and we are assuming pure rolling, so that's important, okay? Pure rolling. Now, to solve this problem, we will start, as always, we will start with a figure. We'll draw a figure of this tire, including these points, A, B, C, D, and the middle, M. Okay, and now, as we just discussed, we know that point A is identical to our velocity pole. If that is our velocity pole, the velocity is 0. For the points B, C, and D, we first need to find the angular velocity omega if we want to solve this problem using the velocity pole approach. So how can we do that? We have the velocity and the acceleration of the car, which is given. So right here, on to our velocities, we know that our car, if it travels with 10 kilometers per hour, the center of the tire, the axis of the car travels with 10 kilometers per hour as well. Now, knowing this, we can use the approach for the velocity pole, because now we know that Vm can be described as pure rotation about point A, and this is radius, distance from M to A, times angular velocity, exactly, r times omega. Vm is given 10 kilometers per hour. The radius is given in centimeters, so we have to convert it to meter. We have to convert the kilometers per hour to meter per second. And once we've done that, we can obtain omega. I haven't computed it yet. Just a second. Or if one of you has the result, then can write it in the chat. I didn't. So what we want to do is Vm over R. .31 should be 8.96. Ah, yeah, thanks. 8.96 per second. So that's our angular velocity. And then once we have the angular velocity, we can compute the velocity of points B, C, and D. For point B, we need this distance. Now, we know that this is the radius, and this is the radius, our triangle with right angle, and then this distance right here is square root of 2 times r. So Vb is equal to square root of 2 times r times omega. R times omega is Vm. So it's square root of 2 times Vm. And that's 3.93 meter per second. And due to symmetry, that's also the velocity for point D. The same distance between the points D and A, so this is also Vd. If we draw it here, this would be VB, and this would be the absolute velocity of point D. So we only need point C, and for point C, the upper position of the tire, we have 2 times R times omega, or 2 Vm, and that is 5.56 meter per second. Pointing that way. BD. Yes, exactly. BD is equal to BB due to symmetry. No, Vm is 10 kilometers per hour, but we had to, I converted into meter per second. Okay, so 10 kilometers per hour is 2.7378, yeah, thanks, meter per second. Okay, but now, as we already discussed, we are only able to compute the velocities using the velocity pole. For the acceleration, we have to use our standard approach. So here we have to say, or we have to compute the components, translational and rotational components. So to do that, I will draw the tire again at the center, and then points A, B, C, and D. And well, maybe I will solve it for the velocities in the standard approach as well, for you to have both options, to see both possible solution paths. So let's do the velocities again. Now, again, we do know that we have the velocity Vm here. That's what we know. And now in our standard, in our general approach, we will say any other point on this object moves translational as our center of gravity. So we have Vm, 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 Vm. And at the same time, these points A, B, C, D rotate about the center of gravity. V, Cm, V, Dm, Vam, and Vbm. Now, in this case, there's one important information we need to know. In case of pure rolling, the relative velocity, sorry, wrong color. The relative velocity in the contact point between object and surface is 0. So that's what we have to know. VA is equal to 0. And if you know that, we can compute the velocities in this point. 0 is equal to, absolute velocity is 0, and that's translation plus rotation, simple vector addition, since both vectors are parallel. Yes, that in the upper option using velocity pole, we said that VA is our velocity pole. Now we are solving it without using velocity pole. So here for point A, right? I'm talking about point A. Now we can rearrange the equation. VAM is equal VM. And also, since it's the rotation, we said it's always for the rotation distance between the points A to M is the radius R times omega. Then if we know Vm, 2.78 meter per second. Then we can obtain omega, of course, with the same value, 8.96 per second. C get the same what? Same size of the velocity? No, because it's a different distance. 2 times the radius. We will see this here in the example as well. Okay, we know the now in our second approach, we were also able to compute the angular velocity, and with this we can do our vector addition for point B. VB, simply adding these vectors, green and purple, okay? VB is equal to VBM square plus VM square. And then this results to 3.93 meter per second. And of course, again, it's identical for point D, since here the two vectors are perpendicular to each other as well. Then for point C, both vectors point in same direction. So VC is equal to VM plus VCM. And then that's 5.56 meter per second. Double in size compared to the velocity Vm, which we can know since VAM and Vm are of same size. So if we add them here, pointing in same direction, it's just like 2 times Vm.
Professor?
Yes?
So I've understood the mathematics behind this question. My only doubt is, for example, you took a very specific methodology. So you started off in the upper diagram and you went from VM to VB to VC. And then you made another diagram specifically for VB. I just don't get it. Why do we
It's
like...
two different, it has nothing to do with each other.
Ah, okay. They're not related.
First option, second option. But with both options, of course, I will obtain the same results. Okay, but with the second option, our standard approach, we are able to compute the accelerations. And for that, I will draw another diagram, same as in chapter 1, draw one diagram for velocities and one for accelerations. Whoops, like this. Now again, we know the acceleration of the center of gravity. It's the acceleration of the car, A. Then all the other points on this object, on this tire, are accelerated translational with the same acceleration A. And at the same time, the tire rotates with omega and alpha. Then in case of accelerations, we have a normal and a tangential component of the acceleration. So start here. That's alpha times r and r omega square. R omega square always pointing inwards. And alpha times r tangential on the path. The vectors itself are always of same size, only the direction changes. Point A, point B, point C, point D. Okay. Now, again, we have to go through one point to the next. And we do know omega already from the computation of the velocities, but we do not yet know the acceleration. But again, we have this point A. And we have this relation saying, okay, our velocity in horizontal direction is 0, and then our acceleration in horizontal direction is 0 as well. Meaning that if we can say that r omega is equal to Vm, our initial, our velocity of the car itself, then this condition is also true in its time derivative. So if we build the time derivative of this condition, times d over dt, we have r alpha, the radius is constant, times a m, or which is our acceleration of the car. We know the radius, we know the acceleration of the car, then we can compute alpha by a over r with that's 6.45 per square second. A is meter per square second, not per second. 2 meters per square second. So 6.45 per square second for alpha. And then again, we can do our vector addition. Yeah, exactly. So for acceleration of point A, we have in horizontal direction and in opposite direction, A minus alpha times r square plus, perpendicular to that, r omega square. And that's 24.89 meter per square second. I'll move it up a little bit. Then for point B, we have pointing in same direction, in horizontal direction, the acceleration itself, and plus r omega square, and then perpendicular to that, alpha times r. And that's 26.96 meter per square second. Yes, exactly. Then for C, we have A plus alpha r square plus r omega square to the power of 2. And that's 25.21 meter per square second. And last one, point D. There, the horizontal components point in opposite direction, so it's A minus R omega square and squared plus alpha R square, and that is 22.98 meter per square second. And that's how it works. Okay, of course, that's our very first example of chapter 2. So it's quite a simple example. It's just one object, our tire, performing a relatively simple form of motion. It's a pure rolling motion, but the principle behind it is always the same: superposition of translation and rotation. And our rotation, our acceleration of the rotation, may consist of two components, so a tangential and normal component, and then we have to do the vector addition. Here in our example, the vectors were either parallel or perpendicular. In more general examples, there might be a different angle between the vectors. But apart from that, there's not much difference. Questions?
Professor, can you please scroll to the second diagram? Up, yes. So over here, let me just annotate. I'm a bit unsure about the direction of VAM and VM. Is this a fixed rule, or how do we determine this?
Well, VM is our translation as the center of gravity, and if the velocity of the center of gravity, our VM, moves to the right, then it has to move to the right everywhere. All our purple vectors pointing in the same direction as our red vector VM. And the direction of the rotational velocity depends on the direction of the rotation. And if it rotates clockwise, then in this point right here, the velocity points to the left, upwards in B, downwards in D. Always tangential on the path in direction of travel. So there's no difference to chapter 1.
Understood. Thank you.
Okay.
Professor, could you scroll down a little bit? Yeah. Okay, thank you.
Yep.
Professor, are you uploading your notes to e-learning, your handwriting notes, or should we take notes?
No, you should take notes, because if you only read my final notes, it will not help you understand. You have to derive it for yourself. And also in the lecture notes, I make a lot of additional notes referring to your questions, explaining your questions. So it will be really hard for you to read at the end. So I hardly recommend that you take notes on your own, just for you to get it straight and understand what's going on.
Of course, but so far I don't want to speak to for anyone else, but I haven't been taking any notes, and
well, that's bad. Well, sorry about that, but that's I cannot help you there. So I think you're old enough to know that in class you have to take notes, and I also talked about it. I gave you lecture notes with blank spaces for you to fill. So I don't know.
Of course.
So if there are notes missing, maybe the easiest way would be talking to your classmates. Okay.
Yeah, that's right. Thank you.
We have 3 parts to, well, no, actually 2 parts, because for the velocity, we have 2 options. For the acceleration, we have only this one option, first and second option. And the second option is a general approach that always works. Yeah. So if you don't like using the velocity pole, you don't have to. Okay, then.
Wait, Professor, if we go to the script PDF, the script. Can you show me page 6?
No, we are not taking pictures of the entire lecture notes now because you came an hour late.
Just one picture.
But just talk to your classmates. You cannot always ask me. You have your group of, I don't know, 197 students signed up in class, and just you need to talk to each other. Help yourself. You're not the first one. And every time I have students take me this picture and take me page number 5 and page number 4, we will never finish. And then you have a lot of pictures on your phone, and you will never write them down.
No, I'm writing them
Then-
down. Just now you skip the next page.
Talk to your classmates, please. Okay.
Okay.
Okay. Then have a good weekend and see you on Monday. Bye.
Thank you, Professor.